Hi everyone, this is Mehul Mehta and welcome back to my YouTube channel. So in this video, let's understand the theoretical piece of Nelson Siegel Svensson model, and also I'll be showing you the practical implementation of this model in Excel. Also, we'll be seeing how can we calibrate this model using the market data, and we'll be using techniques such as OLS, which is ordinary least square method to calibrate our model with market data. But before that, let's understand the theoretical piece. So in this video, I'll basically walk you through. I'll basically walk you through what is the Nelson Siegel Svensson model. So the Nelson Siegel Svensson, I'll just represent this by NSS. Okay. So I'll basically give a quick introduction about this NSS model. So we'll see what is Nelson Siegel Svensson model. Then we'll see why was the model developed. Okay. And then we'll see the mathematical formula or the mathematical framework of this model. Okay. Followed by what is the what does the so when I say mathematical framework, that basically means mathematical formula. And in the mathematical formula, there are different components of it. So we'll understand what are the interpretation of the components, followed by what are the advantages and certain limitation of this NSS model. Advantages and limitation of NSS model. I'll be also showing you how can we calibrate the NSS model with market data using OLS technique. OLS is nothing but ordinary least square method, and in the end we'll see the Excel implementation of the Excel implementation of the NSS model. So this is the objective of this video. Okay, so let's start the introduction. So let's see the introduction of the NSS model. The NSS model, which is the Nelson Siegel Svensson model, is an extension of an Nelson Siegel model. Okay, so this is a Nelson Siegel Svensson model is an extension of Nelson Siegel model, NS model. Okay, Nelson Siegel Svensson model is used in finance to model the yield curve. Okay, to model the yield curve. So this model, the NSS model, was developed in 19 it was developed in 1994 by Lars Svensson. So what happened was, if you see, okay, so first of all, if you have not seen my Nelson Siegel video, I highly recommend to watch that, because Nelson Siegel Svensson is an advancement or an extension, you can say. So Nelson Siegel Svensson is an extension of Nelson Siegel model. So if you don't understand what is Nelson Siegel model, you won't be able to appreciate the beauty or appreciate the implications of the Nelson Siegel Svensson model. So I would highly recommend to watch my previous video on Nelson Siegel model. Okay. So what happened was, in 1987, the Nelson Siegel model was developed, and in 1994, Nelson Siegel Svensson model was developed. Okay. See, always remember, whenever a new model is developed, it is developed so that it can basically So Nelson Siegel might have certain flaws, right? And that's why, and that's why this NSS model was developed so as to cover all the flaws of Nelson Siegel model. Okay. So see, Nelson Siegel model had certain flaws, which was actually captured by Nelson Siegel Svensson model. Okay. So let's understand why was this model developed. And in this, we'll speak about the flaws of the Nelson Siegel model. Okay. So let's see why was this model developed. So if you see the Nelson Siegel model, the Nelson Siegel model, it could only capture single hump in the yield curve. Okay. So if you see, let's say we have a yield curve something like this, right? So let's say if you have so this is what you say as hump or dip. Okay. So you can also have something like this. Or let's take this example. Okay. So if you see this part, or if you see something like this, okay. If you see some hump or if you see some dip, okay. This was effectively, if so in the yield curve, if there was just a single hump, if there was just a single hump in the yield curve, it was effectively captured by the Nelson Siegel model. But where was it failing? It was failing. It was failing when we had more than two humps, or when we had more than one hump or dip. So what if you see something like this, right? What if the yield curve goes something like this, where you see two dip, or they can be two humps like this, right? So in this case, where you see two hump or two dip, right? In this case, the NS model was failing. Okay. And that's where NSS model came into existence in 1994. Okay. Which could capture, two or more humps. Okay. So the Nelson Siegel Svensson model, if you see, if there are humps, if let's say there are two humps, right, like this, or two dips like this, it can effectively capture such shape. Okay. So let me rewrite this. Okay. So if you see, Nelson Siegel model struggled to capture complex shapes of the yield curve. Okay. So when do you see complex shapes? When do you see shapes which are complex in nature? During economic stress. Okay. So when do you see such shapes? During economic stress, right? Or during when if there's any unconventional monetary policy, unconventional monetary policy announcement. If certain, or let's say any, if you see COVID period, which was 2020 pandemic, right? So all in such cases, the shape of the yield curve, like we saw something like this, in general, right? What do we see? We see something like this, or we see something like this, which is, the normal shape of the yield curves, right? But in complex, in, economic stress, that's where the shape of the yield curve becomes, very complex in nature, and that's where we need, certain models in place which can capture these complex shapes. And that's where Nelson Siegel Svensson model does a pretty good job. Okay, so just to make you understand this Nelson Siegel Svensson model, so Nelson Siegel model was actually struggling to capture complex shapes, and that's where Nelson Siegel Svensson model, and that's why Nelson Siegel Svensson model came into existence, so as to capture complex shapes. Okay. So let's see the mathematical formulation or the mathematical framework of Nelson Siegel model. Okay, sorry. Let's see the mathematical framework for Nelson Siegel Svensson model. Okay. So let's see the mathematical framework for this, or let's say the mathematical formula for this. See, if you all remember from my previous video, which I have done on Nelson Siegel. Okay. So the formula for Nelson Siegel was, let's say, SM, which is the spot rate at a given maturity. It can be defined as beta naught plus beta 1 times 1 minus exponential raised to the power minus lambda m divided by lambda m, okay, plus beta 2 times, again we'll write the same component, 1 minus exponential of minus lambda m divided by lambda m minus exponential of minus lambda m. Okay, so this was, if you see, this was the formula for Nelson Siegel model. Okay, where Sn is what, the spot rate or the rate at a given maturity. Okay, beta naught was what, beta naught was the level, long term level, right? Beta 1 was what, beta 1 was the slope, and beta 2 was what, beta 2 is nothing but the curvature. Okay, and lambda was what, lambda was the decay factor. If you have not seen my video, I highly recommend please go and watch it, because I've actually told in detail what does each components mean in the Nelson Siegel model. See, this was what Nelson Siegel model was, and M is nothing but the maturity. Okay, so what Nelson Siegel Svensson did, he kept the same formula as it is, but he also added one more. So he kept the formula. If you see this formula, he kept that formula as it is. He kept this formula as it is. He did not change anything here. Just whatever you see here, he kept it as it is. Just he added one more component. So let's see what that component is. So he just added this component. Okay, so let me rewrite this Nelson Siegel Svensson formula so that you guys do not get confused. Okay, so the Nelson Siegel Svensson formula is what? It is same as, okay, let me write this. Sm is equal to beta naught plus beta 1 times 1 minus exponential of minus lambda 1 t or lambda 1 m into lambda 1 m, sorry, divided by lambda 1 m plus beta 2 times 1 minus exponential of minus lambda 2, sorry, minus lambda 1. So this will remain the same, right? Lambda 1 m. Okay. Up till here, if you see, this is exactly the same. Only thing that I have done is, okay, yeah, my bad. I just missed one more thing. Minus exponential of minus lambda 1 m. Okay. So if you see this equation and this equation, if you see these two equation, okay, let me zoom in. Oops. Sorry, let me zoom in both of them. Okay. So if you see both the equation, only thing that I've changed is instead of lambda, Instead of lambda, I have written lambda 1. Okay, that's it. Otherwise, both the equation look exactly the same. I have not changed anything. It looks exactly the same. Okay. So what Nelson Siegel Svensson did extra. Now let me write what he did extra. He included one more term plus, okay, plus beta 3. And this he wrote the same thing. If you see in the equation, he wrote the same thing. Only thing that he changed was instead of lambda 1, he did lambda 2. So the this equation is what? Okay. So this is what his equation was. So if you see this whole equation up till here, if you see this equation was nothing but a Nelson Siegel model, and this is nothing but he added this term, and this whole equation became Nelson Siegel Svensson model. So just make sure you understand this was nothing but a Nelson Siegel model, and he added this term. Okay, he added this term. So okay, so let me explain you what is the components. Okay, what is beta naught, beta 1, beta 2, beta 3, lambda 1 and lambda 2. Okay, so let me explain that to you. Okay, so beta naught, so we have how many components? Okay, so we have beta naught, beta 1, beta 2, beta 3, lambda 1, lambda 2, m. Okay, so these are the these are the input parameters of this model. So let's understand what are these and what does it mean. Okay, so beta naught is nothing but it represents the long term mean, or it represents the long term level, or you can say it represents the long term yield level. So what do I mean by that? So let's say everything else being zero, let's say beta naught is 4%. Okay. So how will my shape of the yield curve will look like? This. That's it. Just a flat curve. If let's say beta 1, beta 2, beta 3 are 0, right? And beta naught is 4%. My this is how the shape of my yield curve will look like. So this is nothing but it represents a long-term level. Okay. So this beta naught represents the long-term yield level. Okay. So this is what is beta naught, which comes here. Okay. This is what is beta naught. Let's see what is beta 1 and beta 2. Okay. So let's see what is beta 1. See, beta 1 is nothing but it is also called slope. Okay. It is called slope, and it represents, or it captures the steepness of short-term maturity. Okay. So basically, let's say if you see any yield curve, right? If you see any yield curve, let's say something like this, right? So if you see this steepness, so so this is what beta 1 captures. So it captures the steepness of the short-term maturities. So, so if you see any yield curve, right? It will have 1 month, 2 month, and so on up till 30 year, right? So whatever steepness that you see in short-term maturity, that is what is captured by beta 1. Okay. So the steepness of short-term maturity, right? It is captured by beta 1. Okay. I hope you understand this. And in the end, I'll give you very simple example so that you can understand all the parameters at once. Okay. I'll give you a live example. So this was beta 1. So let's see what is beta 2. So if you see, we covered beta naught, we covered beta 1. Let's see what is beta 2. See, beta 2 is nothing but, if you see, beta 2 is nothing but it is also called curvature, first of all. It is also called curvature. Okay. And what it does, it okay, so what it does, it models or it captures the medium term hump or dip, or it captures the hump or dip that you see in medium term maturities. What do I mean by this? Let me give you an example. So let's say your yield curve is something like this. Okay, your yield curve is something like this. So this dip, or let's say something like this, you know, this hump or this dip, you know, how will you model this or how will you capture this? So this part is actually been captured by beta 2. Okay, this part has been captured by beta 2. So it captures the hump or dip, that you see in the medium term maturities. Okay, that you see in the medium term maturities. This is very important. Okay, hump or dip in medium term maturities. And what was beta 1? Beta 1 was basically steepness of the short term maturities. Okay, and beta naught was nothing but the long term of the yield curve, or long term of the yield level. Now let's see what is beta 3. See, beta 3 is nothing but the second curvature. Okay, it is called the second curvature. See, remember this thing, the beta 2 is called the first curvature and beta 3 is called the second curvature. So what it does is beta 3 helps you to capture a second hump or dip, okay, in the yield curve. So let's say you see something like this, okay, in the yield, okay, my bad, in the yield curve. So you see something like this. You see your curve going like this, then you have one dip and something like this, right? So now if you see this part and this part, so this part is captured by beta 2 and this part is captured by beta 3. Okay, so the first hump is captured by beta 2, the second hump or second dip is captured by beta 3. Similarly here also, first hump or first dip is captured by beta 2. So I hope this helps you understand you know how this Nelson Siegel model was better than or let's say how this Nelson Siegel Svensson model was better than Nelson Siegel, because if you see in Nelson Siegel model there's this extra term which is what, lambda 3 beta 3, sorry, my bad. So if you see this Nelson Siegel model, this was the extra term, if you all remember, right? In the Nelson Siegel Svensson model, this was, if you see, this was the extra term, right? This was our extra term as compared to and what if you see if you see this one, the one marked in red, this was already our Nelson Siegel model, and basically in the Nelson Siegel model we added this, and effectively it became Nelson Siegel Svensson. So what did we add? We add beta 3. What does beta 3 does? Beta 3 basically captures the second hump or the second dip. Okay, it captures the second hump or the second dip. And lastly, we have what? Decay factors, which is lambda 1 and lambda 2. These are called decay factors. Okay, so what does it mean by that, or what does lambda 1 lambda 2 signifies? See, lambda 1, it controls how quickly the curvature effect, which is what, beta 2, will fade as or will fade along the yield curve. Similarly, what is lambda 2? It controls how quickly the second curvature, which is what? Second curvature is what? Beta 3. Why? See, if you all remember, first curvature is beta 2 and second curvature is beta 3. Okay? So what is so lambda 2 is for? So lambda 1 is for beta 2 and lambda 2 is for beta 3. Okay? So it controls how quickly the second curvature will fade. Okay? So I hope you understand. And let me summarize this. So basically beta naught is nothing but a the long term level of the yield curve. Okay? Then we have beta 1, which is nothing but the slope of the yield curve. If you all remember, if let's say this is how the slope looks like, then basically this part, the starting part, right? How steep it should be, that is defined by beta 1, steepness of short term maturity. Similarly, beta 2 is what? Beta 2 is the first curvature. Okay? So let's say if we have a dip like this, so this is what is captured by beta 2. Similarly, beta 3 is what? The second curvature. Curvature means it can be a hump or a dip. So let's say, so this is a hump and this is a dip. Okay, this is a dip and this is a hump, right? So the second, so if you see what does beta 3 captures, if let's say there are, so let's say there are two dips, let's say. So beta 2 will capture the first dip and beta 3 will capture the second dip. So basically beta 2 captures the first curvature, beta 3 captures the second curvatures. And what is lambda 1 and lambda 2? It is nothing but it tells you how quickly the curvature will fade. How quickly this the curvature, which is what? This part. How quickly this part will fade. Okay. If you see what is this, right? So how quickly this, if you see this part will fade. How quickly the curvature will fade. So if you see for the first one, which is beta 2, for that we have lambda 1 and for beta 3 we have lambda 2. Okay, so for lambda 1 we have, sorry, yeah, for beta 2 we have lambda 1 and for beta 3, which is the second curvature, we have lambda 2. So always remember lambda 1 is for the first curvature, which is nothing but beta 1, and lambda 2 is the second curvature, which is how fast. So decay, so lambda 1 is the decay factor for first curvature and lambda 2 is the decay factor for second curvature. And what do I mean by first curvature? Beta 1, which is the first hump or dip, and beta 2 is the second hump or dip. Okay. So now let me give you a simple example for all of you to understand, or understand or visualize each of these, beta naught, beta 1. So let's say beta naught is nothing but, let me give you this example, simple example to understand the parameters. Okay. So the first thing is beta naught, which is nothing but the level. So if you see what is beta naught, see, just imagine, let's say there is a flat road. There is a flat road. Okay, there's a flat road. This is what is beta naught. Okay, now second is beta 1. So let's say this is the slope. Okay, how will you understand, how will you remember beta 1 is nothing but the steepness of a hill, the steepness of the hill at the start of the road. Okay, at the start of the road. So let's say, if let's say this is how your hill look like, right? This is how your hill actually look like. But let's say the steepness, this steepness at the start of the yield curve is what is beta 1, or you can say the steepness of the hill at the start of the road. So I'm just giving you a simple example so that you all remember. Beta naught is nothing but a flat road, beta, and then beta 1 is nothing but steepness at the steepness of the hill at the start of the road. Okay, so it's just think like, we are going on a journey. In initially there are flat roads, and that's where from where we see mountains. That's where you see the steepness of the mountains, right? And or steepness of the hill, right? So that's where this steepness is. So this, if you see this part is nothing but your beta naught, and then when you see the steepness, this is beta 1. Okay, so this, okay, so beta 1 is basically nothing but the steepness of the yield curve at the start of the, or at the shorter end of the maturities. Okay, so this is nothing but steepness of yield curve. So this is beta 1. Now beta 2 is what? If you all remember the first hump or dip, right? So you can always remember this beta 2 as the bump or hump in the middle of the road. The bump or hump in the middle of the road. Okay, so let's say you are going like this, and suddenly you see a dip, or suddenly you see a bump. Let's say you are going like this and suddenly you see a bump like this, right? And that's what is your beta 2. Similarly, beta 3 is what? Your second hump or dip. You can also, or you can always say the second bump or dip that you faced in the middle of the road. Okay, and the last piece, which is lambda 1 and lambda 2, right? This is nothing but how fast the bump, how fast bump decays. Sometimes the bump will be small, sometimes it will be big, so it depends how fast this. So if you see the first bump, so lambda 1 basically tells how the first bump will decay, and lambda 2 will tell you how the second bump will, how fast will it decay. Okay, so that's with a simple example of how to understand these parameters. So let's see certain advantages of using the Nelson Siegel Svensson model. See, we all know for a fact that Nelson Siegel Svensson model can capture complex shapes. Okay, so we can capture, or we can model complex shapes of the yield curve. Okay, as compared to the Nelson Siegel model. So this is the first advantage. The second advantage is it provides a smooth representation, okay, of the yield curve. See, because see, what do I mean by smooth representation of the yield curve? See, if you see, we have various components, right? Beta naught, beta 1, beta 2, beta 3. We have then lambda 1, lambda 2. See, using these parameters, we can basically understand mm, why do we see a specific shape of the yield curve, right? Using the parameters, right, of this model, we can understand why we see the yield curve in a certain way, right? And that's why this model, that's this model helps us to interpret the shape of the yield curve. That's why it helps us interpret the shape of the yield curve. Okay. So these are certain advantages of, why do we use the Nelson-Siegel-Svensson model. Also, let me walk you through certain limitations of it. See, all the models that you see in the world of quantitative finance will have certain advantages. Also, it will have certain limitations. It is not always the case that, oh, one model is perfect and it can be used for all the scenarios. It will never happen that. Whenever you see in quant finance, you will have multiple models. So even for yield curve modeling, we have multiple models. So it is not necessary that one model is will use only one model, and you should not remember or understand the rest of the models. Each model is very important. Every model is very important because right now let's say you might be using some model, let's say model X, but it can happen that in the future the environment has changed so drastically that model Y has become more important. And that's where understanding which model is important and when is it important is very this is like very important piece for all of you to know. So what is this limitation of the Nelson Siegel Svensson model? See, the first limitation is overfitting. So risk of overfitting. See, we always want a model which can. So if you see in the Nelson Siegel the Svensson model, we included beta 3 and lambda 2. These two terms we included, right? But also with inclusion of these, right, it can also increase the risk of overfitting. And we do not want to overfit the curve, okay? We do not want to overfit the yield curve. We always want to understand what is the right shape of the yield curve. We do not want to just match whatever it is, right? Instead, we should understand what should be the correct shape of the yield curve. So that's why it's important that the model should not overfit the yield curve. Second is para, so it's parameter estimation. See, the thing is in this model, if you see, we have six parameters, right? Which is beta naught, beta 1, beta 2, beta 3, lambda 1, lambda 2. So we have to, always, whenever we use this model, every time we have to basically optimize these six parameters, right? And this makes our work computationally demanding. Every time we need to find these values beta naught, beta 1, beta 2, beta 3, lambda 1, lambda 2, right? So sometimes it becomes computationally intensive job, okay? So but let me give you a clear picture. Just want to give you a complete picture. So these are certain limitations what you see, but let me give you a complete picture of Nelson Siegel and Nelson Siegel Svensson model. So this is Nelson Siegel model and this is Nelson Siegel Svensson model. Okay. So the first thing is parameters. So see, Nelson Siegel has only four parameters, which is what beta naught, beta 1, beta 2, and lambda 1. Whereas Nelson Siegel has six parameters: beta naught, beta 1, beta 2, beta 3, lambda 1, and lambda 2. So this is the first difference, okay? Then we have flexibility. So if you see, Nelson Siegel model can capture, if you see, this model can capture single, hump, or dip. But Nelson Siegel Svensson can capture much more complex shapes. Okay, it can capture much more complex shapes. Basically, when I say much more complex shape, I mean multiple humps or dips. Okay, and use case is what? Last piece is the use case. Okay, see, when the economy is doing, normal, or it is suitable, or when you see the typical yield curve in the economy or in the financial market, that's where you can use Nelson Siegel model. But if you see, this Nelson Siegel Svensson model it becomes much more efficient for stressed market, because in stress market the yield curve shape differs a lot, and that's where we need much more complex models like Nelson Siegel Svensson as compared to the Nelson Siegel model. Okay, so this was all about what is Nelson Siegel model. Let's look at the calibration of Nelson Siegel Svensson model, and then I'll show you the Excel implementation. So let's see, how can we calibrate Nelson Siegel Svensson model with market data using ordinary least square. Okay, using OLS method. Okay, so OLS is nothing but ordinary least square. If you see the term, you yourself will think, square. We are squaring something. Least. We are minimizing the square, right? If you just see the name, ordinary least square. Square means, just taking the square of something, right? And then what we are doing least, we are minimizing this. So this is what this method is. Okay. So what happens is, from the so we have like different yield, okay, for given maturities. So let's say something like this. So let's say we have yield data, let's say 1 month, 2 month, 3 month, and so on up till 30 years. Okay. Let's say 4%, 4.25%, 4.5%, and up till, let's say, 5.5%. Okay. This is the actual yield. This is the market data that we have. This is already that we have. Okay. Then we will model the yield using Nelson Siegel Svensson. How will we model? If you all remember the formula that we had, the long formula, right? Beta naught plus beta 1 times, if you all remember, 1 minus lambda, if you all remember this formula, right? And so on. So using this formula, okay, using this formula, we will find what? The model yield, which is, let's say this comes to be 3.75%, 4%, something like this, okay? And so on, let's say 5.25%. So now what we'll do, we'll calculate the error, okay? And then we'll square the error. So how will we calculate the error? Actual yield minus predicted all the modeled yield, okay? So what is, if you remember, this was our actual yield and this is our model yield, okay? And we are just differencing it. So 4% minus 3.75%, okay? Which is what? So 4% minus 3.75% is what? 0.25%. Similarly, 4.25% minus 4% is what? 0.25%, and so on. Okay. We'll just subtract the actual yield and the model yield. Okay. So this will give you these numbers, right? And then you just take the square of it. So 0.25 square is nothing but 0.625. So I guess it will be 0.0625. So something like this. Okay. You'll get some numbers like this. Okay. So now what will happen? So now the next thing is you need to sum it. So whatever square error that you get, you need to sum all the square error. Okay. So whatever square error you get, you'll sum all the square error, and then you will try to minimize this value. And this is what is ordinary least square. That, if you remember, what was the term ordinary least square? So what is the square? The square is nothing but the square of the error term. Okay. What is the error? Error is nothing but actual value minus the modeled value. How do you calculate the modeled value? Using the Nelson-Siegel Svensson method. And then we are trying to minimize this square, sum of square. Okay. So so you might be thinking, how can we minimize it? See, we can minimize, if you all remember what we are trying to minimize, the square, the sum of square error. Just think, how can we minimize this error? What can we change? Can we change the actual data, or can we change the model data? Of course, we cannot change the actual yield, right? Because that is what we observe in the market. So we have to change the model yield, right? How will you change the model yield? By changing the parameters. What was our model yield, if you all remember, using our Nelson-Siegel-Svensson method? We had this mathematical formula, and using this mathematical formula, we were calculating the model yield, right? But so what do we need to change? We basically need to change these parameters. So will be so the goal is to optimize these parameters in such a way. So when I say optimize, basically you need to find the values of these parameters in such a way that the s- that the square that the sum of square error is minimized, and that is what the goal of ordinary least square method. So what this method basically does is, it basically minimize this sum. So it basically, if you see, it minimize this sum of square error. How? By changing these values. So it will do like multiple iterations. It will take like a lot of random values of all of all these parameters, and finally it will select those values where the sum of square error is the lowest. So if you see, this is what is OLS, calibration of our Nelson-Siegel Svensson model using the ordinary least square. So let me write the steps again, so that you guys can remember steps. So the first thing is calculate the difference between the actual yield and model yield. What is the model yield? How do you calculate the model yield? Using the NSS model? Okay. So the first thing is calculate the difference. Then the second step is square the difference. Okay. Third step is sum the square difference. So if you see, you first calculate this error term, right? This error term, then you square this error term. Okay. And then you take the sum of it. Okay. So take the sum of this square error. Last piece is run solver in Excel such that it optimizes the value of beta naught, beta 1, beta 2, beta 3, lambda 1, lambda 2, and minimizes the error term, the sum of square error. Okay. So this is nothing but steps for OLS. Okay. Steps for OLS. Okay. So guys, this was all the, all the theoretical part. Let's move to the more exciting part, which is the Excel implementation. So let's focus on Excel implementation. Okay, so let me share my screen back. Okay, so let me share my screen back. Okay, perfect. So this is the Nelson Siegel Svensson model. Okay, and let me show you how we can use this model. Okay, so if you see, so this is our Nelson Siegel Svensson model. Okay, so this is what the model is, and this is how the Excel implementation spreadsheet look like. Okay, let me give you a quick walkthrough. So this is basically, I hope you can all see the screen. Okay, okay, so this is basically the data that we have from the market, right? Or you can say the actual data that we have. So you might be thinking, how can we get the actual data, right? So let's say, so we have, you can go on to this website, which is the daily treasury par yield curve rates. Okay, this is where the US Department of Treasury, they post the actual data. And if you see, every day they'll be releasing the data every day. So every day you'll see um, some or the other, you'll see every day will have the actual yield, right? So if you see, these are the maturities, the 1 month, 2 month, 3 month, and so on. Okay. Okay, so these are the maturities, and for a given maturity, the US Treasury, they tell what is the yield for a given maturity. Okay, for 2 month they have given this, for 30 year they have given this, and like this, you have like so many years of, or so many months of data. But we need just 1 day of data. We are not trying to forecast anything. We are instead, the goal of the Nelson Siegel Svensson model is to fit in the yield curve. Okay, we are not trying to predict the yield curve, we are trying to fit the yield curve, because that is very important for risk management and bond pricing. Okay. Okay, so coming back to our spreadsheet, okay, this is the Nelson Siegel Function model. So if we see, for like how we see dates here, so I basically took the data for November 2024. Okay. Uh, and so this is how, the maturities look like. It is same as what you see here, 1 month, 2 month, 3 month, and so on up till 30 years. And similarly, you'll see this, and then if you see, we have the actual yield, right? We have the actual yield. So this data is given by the US Treasury government. Okay, this data is given by the US Treasury government. Now the next steps, which is how can we implement the Nelson Siegel Svensson model, and can understand like how can we fit in the yield curve. Okay. Okay, so if you see, this is already given to us, right? If you see, I've just copy pasted the data from here till here, from here to here, and then actually you'll have copy from here to here. Okay, so I've just copy pasted the data. Okay, as you all know, we just covered what is, how can we perform the calibration using the OLS method. So we'll do the same thing, we'll do the same calibration. Okay, so if you see, okay, so a quick thing is for maturity, which is like 1 month, 2 month, 3 month, and so on. Because it is in month, so we need to make sure that all these are in years, right? So how can we convert month into years? Because there are 12 months in a given year, so I can just write 1 by 12. Similarly, if you see, I can write 2 months as 2 by 12, 3 months as 3 by 12, and so on, 6 months as 6 by 12. And if in case something is given in a year, we'll just take it in year only. So we are converting everything into year. Okay, so this is the first thing. Actual yield is already given from the website. Okay, now if you see, this is our formula for Nelson Siegel Svensson method, right? So if you see the components, what I have done is, I have divided this whole model into three components. So the first bracket that you see, which is 1 minus exponential of minus lambda 1 t divided by lambda 1 t plus, so this is the first component or the first bracket. Everything that you see inside the first bracket, I have considered that as term 1. Everything you see inside the second bracket, which has been multiplied by beta 2, I have considered that as term 2. And similarly, whatever you see in the third bracket, which is being multiplied by beta 3, I have considered that as term 3. Okay, so if you see, let's try to model term 1, term 2, term 3. So term 1 is what? If you see, 1 minus exponential of, if you see, I have written the same thing, 1 minus exponential of, if you see, lambda 1 times t. So if you see, q6 is my lambda 1. Okay, so if you see lambda 1 times t, what is my t? T is nothing but my maturity. So just one quick thing is, in the formula, when I was writing the formula, I have written lambda m or lambda t. It's just the same. M means maturity, t also means maturity, you know. So it's just the same. Don't get confused. Okay, so um okay, so 1 minus exponential of 1 minus exponential of minus lambda 1 times t. So f2 is my t and lambda 1 is this which is q6, which I'm taking from here. Okay. Similarly, this divided by what? Lambda 1 times t. So I've again done the same thing. This is my lambda 1 and this is my t. So this was my first component, which is term 1. Okay, now what is my term 2? The second bracket. Okay, so if you see this, I have just used the same, I've just implemented this, which is 1 minus exponential of, again 1 minus exponential of this lambda 1 times t, minus of lambda 1 times t divided by lambda 1 times t, and then again this whole subtracted from exponential of minus 1 lambda times t. So sorry, minus lambda 1 times t. So this is, term 2, which I have, just, if you see this bracket, second bracket, this is what I have implemented. And similarly, term 3, if you see, this is nothing but I have implemented the third bracket. Also remember, in first and second bracket we'll be using lambda 1, and in third bracket we'll be using lambda 2. So if you see this term 2, we are using lambda 1. Okay, similarly, if you see term 1, we are using lambda 1, but for term 3 we'll be using lambda 2, because that's what the formula defines. Okay, so again, we'll be implementing this formula, 1 minus exponential of lambda 2, which is this factor, times t, okay, which is again nothing but our maturity. And and similarly again, this whole divided by lambda 2 times t minus exponential of lambda 2 times t, right? So this is what is the formula, right? So always remember, maturity in our case is t, and this is like lambda 1 and lambda 2. So we have implemented term 1, term 2, term 3. Okay. Now, can I write this the same formula as something like this: beta naught plus beta 1 times term 1, right? Plus beta 2 times term 2 plus beta 3 times term 3. Can I write this, the above formula, in this way, right? Can I write in this way? Why? Because if you remember, term 1 is what? My bracket 1. Term 2 is what? My bracket 2. And term 3 is what? My bracket 3. So I've just multiplied term 1 with beta 1, term 2 with beta 2, term 3 with beta 3, and added b naught. So it's the same formula. I've not changed anything, but just to simplify the formula, I've written something like this. So I'm doing a very similar thing. So I've just done beta naught, which is, if you see, q2. So this is beta naught plus q3 is what? My beta 1. Okay, this is what is my beta 1 times h2 is what? If you see, term 1. Then again q4 is nothing but my beta 2. And what is i2 is nothing but my term 2. Okay, and again q5 is nothing but my beta 3. This multiplied by j2 is nothing but my term 3. So I've implemented the Nelson Siegel Svensson formula as like this. Okay, and then what you have to do, again, what you have to do, you have to just use the same formula everywhere. You just have to use the same formula everywhere to model the Nelson Siegel Svensson. So this is basically the yield that you get using the Nelson Siegel Svensson model. So make sure you implement the same formula everywhere. for all the maturities. Implement the same formula for all the maturities, right? So this is how you calculate the Nelson yield through the Nelson Siegel Svensson model. Okay, so one more thing, which I let me do that. Okay. Okay. So something like this. Okay. So let's say, if you see the OLS method, what was the OLS method? In the OLS method, what was the first thing? The first step was to calculate the difference between the actual yield and the model yield, right? And once you calculate the difference, we need to square it. So I've just, squared. So I've just calculated the difference between the actual yield and the model yield using. So the model yield is nothing but the yield that we got using the Nelson Siegel Svensson model, and just squared all these terms. If you see, just squared all these terms. So we have calculated the error. So this is nothing but the square error. Okay, this is nothing but the square error. Okay, so we have calculated the square error, and then what do we have to do? The next step, we have to do sum of the square error. So this is how you calculate sum of the square error using the OLS method. Now the next step is to what? Optimize our parameters. So if you see, what is the next step? The next step is to optimize our parameters in such a way that this error minimizes. So what do you see right now? This error is how much? 0.782. So we need to minimize it. So what we'll do is we'll do data, we'll go to solver. So what I'm saying is just minimize this L15, which is this. Okay, minimize this, and what do you need to do? You need to change what? Please change these parameters. If you see, please change these parameters. Okay, this is what we have done, and just say solve. Now if you see, just I just did solve. Now if you see, initially before, the sum of square was zero point 0.5 or zero point 0.8, something like that, right? So let's say this goes to 4. Okay, I'm just saying. Okay, now just look, what is the sum of error term? 1.053. Okay, so I'm again using the solver to solve it. And now you see, we have got the optimized value in such a way that the sum of the square error has been minimized. Earlier it was 1, right? And now it is 0.196. And even if you see, the fitting of the yield curve is the Nelson Siegel Svensson model is very close to the actual yield, right? So this is how these models are being used to basically fit in the yield curve. So now you might be thinking, like, if the yield curve is already given, if the actual yield curve is already given, what's even the need of, using these models? Just why should we, why can't we just take the data that we already have, right? You might be thinking this in your mind, but always remember one thing. See, we have data for 1 month, 2 month, 3 month, 4 month, but what about the 5 month? Right? What about 5 month? Let's say we have data for 6 month and 1 year. What about the in between months? What about 7 month, 8 month, 9 month, 10 month, and so on, right? Similarly, let's say if I want to calculate for 1.5 months, so how can I find the data? Because there is no data available for 1.5 months. Even if you see the website, we have data for 1 month and we have data for 2 months, 3 month, 4 month. Now, if you see, there's no data for 5 month. We just have for 4 month and 6 month. Similarly, we have no data for 1.5 month. Similarly, if you see between these 2 years, 20 and 30, we have no data for 21 year, 22 year, up 23, 24, and so on. So that's where all such models are being used to calculate what is the yield for all the missing maturities. Okay. So let's say if I want to calculate what is my yield for this given for 1.5 month, how will I calculate? First thing is divide 1.5 by 12 so as to convert that into year, and then do the same thing. Calculate term one. Now with this, now calculate term one. If you see term 2, we are using the same formula. We are not changing anything. We are just using what, if you see what we did for here, term 1, term 2, term 3, I have just used the same formula here also. I have not changed anything. So after calculating term 1, term 2, term 3, how will you calculate the Nelson Siegel Svensson model or yield at this maturity? Simple, beta naught plus beta. So if you see beta naught plus, if you see what is this q2, beta naught plus q3 is beta 1 times H18 is what? Term. So H18 is what? Term 1, right? Q4 is nothing but beta 2. What is this H I18? I18 is nothing but term 2. and this Q5 is what, my beta 3. And what is this J18? J18 is nothing but term 3. So you have I have just used the same thing. I have not changed anything. And this is how you can calculate the yields at the yield using the Nelson Siegel Svensson model at maturities which are not published by the government. Okay, if you see this data is published by the US Department of Treasury, but if in case there is no data available, you can use all such models to basically tell how much yield will be at a given point of time. So like this is how I have done. So what I have done is I have actually taken all the maturities. If you see in here, we have, like, there are so many missing points, right? Between 6 month to 1 year, there's 7 month, 8 month, 9 month, 10 month, 11 month. Similarly, between 3 to 5 years, 4 year is missing. 7 to 10 years, 8 and 9th year is missing. 10 to 20 year, 11, 12, 13, 14, and so on, right? All these years are missing in the yield. The yield for given maturities are missing. And as I've calculated, I have taken, this all the maturities. Just make sure that for 1, 2, 3 up till 11, you need to first convert them into year. First convert them into year, okay? And then just calculate this. Just calculate term one, term two, term three, and that's it. And then you model yield using your Nelson Siegel Svensson method. Okay, so this is how you can basically calculate the yields at Nelson using the Nelson-Siegel-Svensson method, and then in the end you can basically plot the Nelson-Siegel-Svensson yield curve. Okay, so this was, guys, this was all. This was like the total complete picture. Also, one more point which I missed in my Nelson-Siegel video was, I guess, previously there was just one mistake which I realized. So when I was recording that video, there was a negative sign here. And but if you see in the formula, there is no negative sign. So I've updated this curve, the term 2. I've just updated the term 2. But again, this is how the updated Nelson Siegel yield curve looks like. But again, like, coming back to the Nelson Siegel Svensson model, we have already done term 1, term 2, term 3 properly, and we have calculated the yield curve using the Nelson Siegel Svensson, and this is how the yield curve will look like. Few questions that you might have as a fresher is, see this, if you see, this data changes every day, right? This data changes every day. So will the parameters, which is like these parameters, also change every day? The answer to that question is yes, these parameters will also change every day, because every day you need to calibrate your model with the market data. So all this will change. You might be thinking that, Mehul, like, this is not the perfect shape of the yield curve. Okay, and there's still certain difference in the actual yield and the model yield. I understand, and that is correct also. There is a difference, and this is not the best model, which this is not the best mathematical model for modeling the yield curve. But at the same time, it is very important for all of you to understand that at this moment, this model might not be good, but there have been situations where Nelson Siegel model played a really important role, right? So it is not like because right now the model is not giving a good shape, or it is not giving a close fit with the actual data. This model is not good. Please do not think like that. All the quantitative models are equally important. Only thing that you have to keep in mind is certain models are important in certain scenarios. Okay, so it can happen that right now cubic spline, which I'm sure that model will be the best model of all of these. uh, Cubic spline will work really great, but there can be situation when in cubic spline might not work great, right? So just this is just even I had certain doubts like this. But again, just to summarize, Nelson Siegel Svensson model is a mathematical model. Came into Nelson Siegel Svensson came in 1994, and the term 3, if you see, this was the extra term which was added in the previous. So Nelson Siegel's had only term 1 and term 2, but Nelson Siegel Svensson had term 3 also. So that is what is addition, as compared to what you see in Nelson Siegel model. And if in case you want this spreadsheet, please let me know. I'll be more than happy to upload this spreadsheet. Only thing is you guys have to give me 50 comments in this YouTube video, and I'll be more than happy to upload this whole spreadsheet. Also in the coming videos, we'll see how linear. So up till now we saw what is how Nelson Siegel model works, and how Nelson Siegel Svensson model works. Now we'll explore, in the coming videos, we'll explore linear interpolation, cubic spline, and monotone convex. So I hope you are liking this video series, and I wish you all the best. Thank you so much.